Okay, so here is a drastically modified problem, and I would like you to think about this. Take a minute, okay, take a pen and paper and figure out what can be the entering variables, and corresponding to entering variables, what can be the leaving variables. Okay, what variables can be entering, and corresponding to each entering variable, which variable will leave. Okay, so let's do the analysis. So z needs to be maximized. This is for entering variable. If x1 increases, then z increases. Okay, so if x1 increases, then z increases. If x2 increases, then z increases. But on the other hand, if x3 increases, then z decreases. Okay, so this cannot be an entering variable, because trying to increase x3, which is all you can do, because these are currently at 0, the only thing you can do is increase them, and trying to increase them should also increase z, because our goal is to maximize z. It's currently at 10, but we want to go higher. Okay, so therefore I would like to increase x1 or x2. Okay, so possible entering variables, let me delete my work here. Okay, so hopefully we are all convinced of the following fact, that x1 can enter or x2 can enter. It's entirely your choice, and we'll talk about some rules for making choices among multiple possible entering variables. So currently there are two possibilities, x1 or x2. Okay, let's assume x1 enters. So let's fix x1 to be our entering variable, and let's see what variables can leave. Okay, so if x1 is our entering variable, let's start to increase x1. So if x1 is increasing, okay, x4 unfortunately is also increasing. This is something we didn't see in the previous problem. In the previous problem, if we tried to increase the entering variables, these guys were all decreasing. In this case, if x1 is increasing, then x4 is increasing. So as far as x4 is concerned, it says, oh, go all the way up to infinity, I don't care. Okay, so this doesn't place any constraint on x1's increase. What about x5? Okay, thankfully, when x1 increases, x5 decreases. Okay, how much can x1 increase? Well, x1 can go up to 12 divided by 4, that's 3. So this is 12, this is 4. So x1 can go up to 3, and x5, it cannot go up any further, because going up any further will make x5 negative. So x5 says x1 must be less than or equal to 3. Likewise, x6 says x1 must be less than or equal to 3 as well, because if x1 goes up to 3, then x6 goes up to 3. Okay, so now you have two variables, x5 and x6, that both say x1 can go all the way up to 3. Okay, so you have a choice of two leaving variables, x5 and x6. It's up to you which one you choose. You can choose x5 or you can choose x6. Okay? Likewise, you can roll all the way back and say, what happened if I chose x2 as my entering variable? Okay? And I will leave that as an assignment for you. So what happens if I change my entering variable from x1 to x2? Can I do that? Yes, of course, because increasing x2 increases z, so I can use x2. So if x2 is entering, what are the possible leaving variables? Okay, so I would like you to take a minute and work that out. Okay, you can pause the video right now and try and work that out and see if you really understand. Okay, so all right, so let me give you the solution. If x2 enters, then according to x4, x2 must be less than or equal to 7 by 3. Okay, so that's the bound it places on the increase. x5 does not care, because as x2 increases, x5 is also going to increase. This is a plus here, so it's going to increase. So x5 does not give any constraint. It just says go up to infinity if for all I care. So x2 less than or equal to infinity. So that's the constraint x5 gives us, which is not a constraint at all. And according to x6, it says x2 must better be less than or equal to 9 by 4. 9 by 4. Okay, and that's how much you can take it before x6 goes negative. Okay, together, so this is roughly 2.3 bar, and this is roughly 2.25. Okay, so this is a smaller increase, and this is a tighter constraint, so this wins out, and therefore x6 will leave. So if x2 is entering, x6 is the only opportunity for us to have a leaving variable. So x2 tries to enter, then x6 will have to leave. And going back, if x1 tries to enter, then you have a choice. You can either say x5 or you can say x6. Okay? And we'll look at what this means, but right now we are just looking at the basic simplex and we are not going much deeper than that. Okay, so now we are going to roll back. So the previous slide was just one off. So we are just going to roll back to our original problem from Schwartal, and we are going to figure out what's going to happen to the dictionary after pivoting. So recall, we are going to say x1 enters and x4 leaves. Okay, so we are x1 and x4 are exchanging positions, and I would like to find out what's the new dictionary. Okay, and the trick is quite simple. I'm going to invert this guy. So I'm going to say, this says x4 is 5 minus 2x1 minus 3x2 minus x3. So if this is the case, then x1 better be 5 by 2 minus 3 by 2 x2 minus 1 by 2 x3 minus 1 by 2 x4. Did I get that right? Okay, let's say we took 2x1 here and x4 here. Okay, so we just switch positions and divided by 2. So x1 is 5 by 2 minus 3 by 2 x2 minus 1 by 2 x3 minus 1 by 2 x4. Okay, so this is going to be one of the rows. Okay, so this is going to be one of the rows. I inverted it. And now inside x5 there is an x1. Okay, for this x1 I'm going to substitute it with this expression. So x5 was originally 11 minus 4 times x1 minus x2 minus 2x3. This becomes 11 minus 4 times this whole mess. Okay, so bear with me while I write it down and see if you can spot any mistakes I make. I am a very big mistake maker. Minus x2 minus 2x3. Okay, so this becomes 11 minus 4 times 5 by 2, which is 10, minus, so it becomes plus 2 times 3 is 6x2 plus 2x3 plus 2x4 minus x2 minus 2x3, some algebra, so this becomes 1 plus 6 minus 1, 5x2, 2 plus 2, 2 minus 2, 0x3, so 0x3, and that should be it. Oh, plus 2x4. Okay, so this becomes the new value for the row x5, 1 plus 5x2 plus 0x3 plus 2x4. So I'm just rewriting using the problem data. Okay, and if I move on to the next slide, you can convince yourself that this is how it's going to look. So this is the original dictionary. From here, x1 entered and x4 left. Just given this data that x1 entered and x4 left, I can start to update the dictionary to a new dictionary. Okay, and so now you have x1 here and you have x4 here where they should be, and x2 and x3 just keep their places. But because of all the algebra that I did, the entire dictionary has changed. It has changed completely. In fact, in this new dictionary, the solution that I am representing is x2 is 0, x3 is 0, x4 is 0, x1 is actually 5 by 2, x5 is 1, x6 is 1 by 2, and z is 25 by 2, that's 12.5. Okay, in fact, you started with 0, and in one step of pivoting, you have upgraded your z to 12.5. And that's what pivoting is going to do. It's going to try and increase the z in every step. Okay, and note that we haven't changed the original problem. We have just changed what variables go here. So we have changed our basis, we have changed what variables go here. Well, whatever doesn't go here goes here, of course, and that's all we have changed. Okay, and finally the change is incremental. One variable leaves and one variable enters. So every time one thing leaves the basis and one thing tries to enter the basis, or in the other way, one thing tries to enter the basis, one variable tries to leave the basis. Okay, so pivoting gives you this, and this is pure algebra so far. Alright, so now that you have a new dictionary, so this is dictionary 2, okay, after one pivot from dictionary 1, we can do the same operation. So we can say, what are the possible entering variables in this new dictionary? So what's the entering variable? Okay, so if you took a look, you would find that x3 is the only entering variable, because an increase in x3 guarantees an increase in z. On the other hand, x2 cannot be entering and x4 cannot be entering. The main reason is that increasing x2 or increasing x4 is going to decrease z. So these two are going to decrease z. So therefore they cannot be entering. So x3 is entering. So corresponding to x3, then what leaves? Okay, so let's look at x1. So as x3 goes up to 5 by 2 divided by 1 by 2, which is 5, x1 goes negative. So x3 can go up to 5 and still keep x1 non-negative. As far as x5 is concerned, x3 can go all the way up to infinity and it doesn't care. Okay, because x5, this is 0 x3. Okay, so nothing happens. So the constraint you get is x3 less than equal to infinity. And finally, for x6 you get x6 less than equal to 1. So as soon as, x3 less than equal to 1. So as soon as x3 goes up to 1, x6 goes down to 0, and any further, x6 is going to go negative. So finally, looking at it, less than equal to 1, less than equal to 5, and I don't care, less than equal to infinity, this is the winner, and therefore x6 is the leaving variable. So x3 will enter and x6 will leave. Okay, so this summarizes it. So x1 says x3 less than equal to 5, x6 says x3 less than equal to 1, and this says no constraint. So this is the leaving variable. Okay, therefore you do one more step of pivoting. So we started from, this is dictionary D2, and you're going to get a new dictionary D3 from pivoting. Okay, x3 enters, x6 leaves, so x3 is now here and x6 is now here. Okay, and getting from here to here is algebra. Okay, let me recall. So if you want to make x6 leave and x3 enter, you take this row which has both x3 and x6 in it, okay, the entering and leaving variable, and you invert it. So you say x3 equals, okay, 1 plus x2, all right, minus 2x6 plus 3x4. Okay, so in fact x3 equals 1 plus x2 plus 3x4 minus 2x6. So that becomes a new row. Just invert these guys here locally, and in every other row, wherever you see an x3, you have to substitute this guy. Okay, this gets substituted here, and therefore you get this new problem. All right. Okay, so now that you have this new problem, you can look at the solution. So the solution has changed to x2 equals 0, x3 equals 1, because x3 is here now, x1 equals 2, x5 equals 1, x4 equals 0, and x6 equals 0. So these are non-basic and these are basic. Okay, and the objective has increased from 12.5 to 13. So that's this increase. All right. Okay, so we are not done yet. So there's one last pivoting that we have to do. Okay, and you look at this dictionary and you can see what is the entering variable. You can ask yourself now, what's the entering variable? So this is D3, the third dictionary, and you can say, is x2 an entering variable? No. Increasing x2 is going to decrease z. Is x4 entering? Not at all, because increasing x4 is going to decrease z. Is x6 entering? No, because increasing x6 is going to decrease c. So in this dictionary, there is no entering variable, so no choice for entering variables at all. If there is no choice for entering variable, then we are done. And such a dictionary is called a final dictionary, okay? And the objective value of such a dictionary is the optimal solution. We'll prove this. And furthermore, we can read off the solution from this dictionary, and that's going to be the solution from the problem. Okay, that's going to be a solution to the problem. Okay, and the optimal value is read off as 13. Okay, so we have solved the LP by repeatedly starting from an initial feasible dictionary and pivoting. In this case, we needed two pivots, D1 to D2, D2 to D3, and D3 turned out to be final. We are done.